Hi there, it's Manuel for Entagma. Today I want to talk about the ripple solver inside of Houdini. Before we build a nice little pond scene where we use a ripple solver to propagate waves created by raindrops across the surface of a pond, let's quickly dive into Houdini to see how the ripple solver is supposed to work. The ripple solver is just a dynamic solver. So to use this we need a DOP network. So quickly create one. DOP network and dive inside. In there you have this output and nothing else. First we create a ripple solver. The ripple solver is an object that actually solves the simulation connected to the output. But the solver cannot operate without data. It needs geometry to work on. So we have to define a ripple object. And there is one, so create a ripple object, and on this ripple object you find definitions for the geometry to use. So connect this ripple object to the solver. As soon as you do this, immediately you see geometry is appearing, and that is because this ripple object contains default geometry, just to show you quickly how the solver operates. And this is already functional. As soon as I press play, you see that this bump here creates a ripple, and the ripple is propagating. Nice. So how does this work? Well, the ripple solver is just watching two states of the same surface. One is the initial state and the other is a rest state. The rest state is basically the topology, so the undistorted plane. And the initial state is this disturbance here, modeled as this little bump. And this disturbance is what causes a ripple to appear, and then the solver simulates it and makes it propagate across the surface. You have two settings to define these two geometries, the initial subpath and the rest subpath. At the moment both of these are pointing inside this ripple object because, as I said, inside you find default geometry. Let's quickly right-click on this node and say Allow Editing of Contents, as it is a digital asset. And now we can inspect what's inside, and here in this geo network you find just a grid called rest and then this soft peak. And this soft peak creates this bump. And these two different states of the geometry are used by the ripple object, because the rest subpath points to this rest geometry, so the undistorted grid, and the initial subpath points to the default geo network itself. And as the display flag is on the soft peak, this means it points to the geometry version with this peak. And now the ripple solver just looks at the differences between the two states of the geometry and creates its simulation out of the difference. And that makes it easy to work with this solver, because all we have to do to make it solve ripples is give the geometry some disturbance. So let's do this in the rain pond scene. This is a pond scene. In here I have this geometry of a scanned rocky surface, and then I created just a grid to resemble the water surface. So here's this volumetric scan data, and here is the water. And we want to use the water as a medium for the ripples. So let's dive into the water node. Inside I have a grid and I have a transform, because I moved the water a little bit up to find a good place to intersect the geometry. Now, normally what you want to do to create raindrops is using a particle system. But in our case, that's really not necessary, because we don't want to see the individual raindrops fall down and hit the surface. All we want to have is disturbances in this water surface. So what I do instead of using a particle system, I just use a scatter node to generate points. And then I use these points to generate dents in the surface. So the first thing I want to do is lay down a scatter and connect it to this transform. And this just scatters a lot of points onto the grid. Let's quickly turn off other objects to see what happens here. Well, what I want is very erratic behavior. So I turn off relax iterations, and the total count is far too high because I want just a few ripples to appear. So let's go down to 2 here. This creates 2 points. Let's quickly turn on point numbers to see the points better. 2 points on the surface of the water. I want to randomize this scatter node in every frame, because I want the scatter node to create a different amount of points at different locations in every frame. And that can be done using expressions. The first thing to randomize is the global seed, because the global seed is responsible for telling the scatter node where to put the points. If I change the seed, you see the points start jumping around. So it's very easy to make this jump every frame by just putting $F here. $F is a variable that stands for the current frame, and that means now this is updated every frame to another number, and the points are jumping around. But I want to have a different amount of points appearing in every frame, not 2 every time. So it's time for another expression, this time here in this field, total count. At the moment it's 2. Let's use a random expression. Random just gives us a random number between 0 and 1. And we need a seed value for this random value. And I use $FF this time. This is a variable that refers to the simulation frame, so it's a fractional float frame. It's not just an integer like $F, which gives a little bit more randomness. And this expression gives us a value between 0 and 1. But we don't want a value between 0 and 1 because we want, let's say, minimum 1, maximum 6 points to appear. So what I can do is I can just multiply this by 5. That means if the expression evaluates to 0, we will have 0. And if it evaluates to 1, we will have 5. That's nice, but I never want to have 0. I always want to have at least 1 point. So let's put this into parentheses to make it execute first, and then just add 1. That makes sure that it's evaluating to 1 at least in every frame. Okay, that's a valid expression, and now I have a different amount of points every frame. If I click here, I see the result of the expression, and if I step through the animation, you can see every frame I have a different amount of points at different locations because the global seed is animating too. So let's make use of these dancing points to deform our initial surface. I have this water surface, and what I want to do now is I want to create a little bump wherever one of these scatter points appears. I will do so using a VOP. Let's create a VOP, point VOP, put it down, and connect the grid to the first input, because we want to operate on the points of the grid. And then as a second input, we give it the dancing points, because we want to look up the dancing points, and in the proximity of the dancing points we create a deformation. Let's put the display flag on the point WOP and dive inside. Let me give myself a little bit of room for you to see better. So the first thing that I want to do is I want to look up the points from the scatter for every point of this grid. And that can be done with the near point expression. So I get a near point node, and this near point expects an input where it wants to have the geometry to operate on, and then it needs a sample position. So I give it the input number 2, because this is our scattered points, and as a sample position I use the position of these points. So what happens now is, for every point in this grid, this node gives me the index of the nearest point from the scatter stream. And that is what I want, because what I want to form is the distance from all of these points to the nearest points from the other geometry stream. Because if the distance is lower than a certain value, I can use this information to deform this surface. As we are talking about distances, what I want is the position of the nearest scatter point. So to find the p value of the scatter points, I have to look them up with a point expression. So create a point node, import point attribute. And this import point attribute operates like the near point. It needs the geometry. So give it the geometry from op input 2. And then it needs a point number. Now it looks up an attribute at this index here in the second geostream. And the attribute to look up can be put here in the parameters, and by default it's P already, and that is what we want. And you see here this light green color on the result tells you that this is a vector. So now we have P here, which is the position of the point we are currently executing, and then we have this P here, which is the position of the nearest point from the second geometry stream. What we can do with this information is we can find the vector between the 2 points, and then we can just measure the length of this vector to find the distance. So let's create a subtract, and let's subtract these 2 vectors to form a vector between them. And now we can measure the length of this vector, and by doing so find the distance between every point of the grid and the nearest point from the second geostream. So I put down a length node, and this just measures the length of a vector. And as this vector here is between the 2 points, this will give me the length. Let's quickly debug this. So I bind export this result and quickly call this debug. And what I can do now is I can visualize this by creating a visualizer node. Connect this to the visualize, and we say ramped attribute and the attribute to visualize debug. And now we say range is min and max. And what you see here is, well, basically something like a cell noise, because it visualizes the distance of every point of the grid to the nearest point from the scatter stream. And here are the points from the scatter stream. Let me make them visible. Well, they are very, very tiny. Here in the middle, where it's blue, the distance is small, and where it's red, the distance is high. And this can be used to deform the plane. So back to the point WOP. Inside, instead of just binding this to debug, I can use it to deform actually my plane. And that can be done by adding a vector to the original points. The vector I want to add is y up, because I want to have dents go up in y. So I create a constant, typo constant of type vector, and just give it a default of 0, 1, 0, which is y up, and then I need an add node. Add, no, not attrib. Add, please. Add. And I can add this to the position of the points. If I do so, and then connect this to P, what I get is all the points just transformed by 1 unit in y, because this is what this vector is telling. So to modulate this by the length, I need a multiply. And this multiply can be used to modulate the length of this vector here. So if I use the length now, what I get is this. You see? Now I use a distance to deform my plane. But it's not at all what I'm after, because I want the opposite. I want the places where the distance is very low to go out further, and I want to somehow constrain the effect just to the area around my point. At the moment, it's really deforming everything. So let's think about how we can achieve this. What helps us out in this situation is a fit node, because the fit helps us remap a value range, and the value range is just wrong at the moment. What we want to fit is, we want to fit the length. So let me quickly tidy up the network a little bit. Put the fit here, and the multiply there, and the const there, and the length maybe down here. So at the moment, the length is really unclamped. What we want to do is we want to reverse this value, and then we want to clamp it. So we put the fit here. You see, the first thing that happens is that it clamps the values, because fit automatically clamps. There is an unclamped version of fit 2, but the standard fit node clamps at 1. If I go lower than 1 in the output value, you see it clamps even lower. So the incoming range is what helps me restrict the effect to the area around the points. If I go lower here, you see that the effect is really restricted, because now it maps just the distance between 0 and 0.255 to the range of 0 and 1. That means where the distance is 0, we get an effect of 0. Where the distance is 0.255, I get an effect of 1. And outside of this, so whenever the distance is higher than this value, it stays at 1. And if I want to reverse the effect, nothing easier than that, just reverse these two numbers. So I put a 1 here and a 0 there. And now I get this. Because now, wherever the distance is 0, I get an effect of 1. So this vector is scaled by 1, has the full effect. And wherever I have a value of 0.255, I have a output of 0. That means the effect of this vector is not there anymore, because the vector is scaled to 0. So that is one step further, because now with this source max, I can control the radius around my source points. And that is exactly what I am after. What bugs me though is that the shape of these cones is very, very linear. And instead of this linear shape, I would like to have an S-curve profile. So after the fit, what I can do is I can introduce a ramp node. And the ramp parameter node creates a ramp parameter. Standard is an RGB color ramp, but in our case we want a spline ramp because we want to remap a float value. And the ramp itself is created on the point VOP. So if I want to alter the values of the ramp, I have to go up one level. And what this allows me to do is to remap the value range again. So remember, this fit node outputs a range between 1 and 0. And now I can use this ramp parameter that is created on the point VOP, and here it is, to remap this value range. At the moment it's linear. But if I introduce a point here, by just clicking there and then move this point, you see that I can alter the shape, because this shape is just a result of the value range. And I can go down here and maybe go to B-spline, but I have to do this on all the points for it to take effect. Let's do it on all the points. Now I have all the points set to B-spline, and what I can do now is I can really create a very nice soft shape. Look at this. Now I have a very nice fall-off. And that is basically what we want, because what I have now is for every scattered point, I get a nice little dent here in my plane. So if I rewind and make this play, you see wherever these points appear, they create a dent in the surface. Which is great, because now I have everything I need to make the ripple solver work. I have an undeformed initial state, rest state, and I have a deformed, dented state that changes in every frame. So the next step is to create a ripple solver and use it. Okay, so now let's make this happen. As before, let's create a DOP-net. DOP network. I wire this in here. It's not necessary to do this, but for me it's somehow easier to understand if it's wired in. Inside, we create a ripple solver as before and a ripple object and wire it up. Now we have that, and we have to define the objects that the ripple objects is pointing to. At the moment, as before, it's pointing to the default geo, but that is not what we want. So the initial subpath, if you remember, is the distorted geometry. So in our case, this is the point VOP. Let's go up one level just to make sure you remember. The point VOP is our distorted geometry, and this transform here is our undistorted geometry. So, the initial subpath is the distorted geometry, so in our case the point VOP, and the rest sub is the undistorted geometry, in our case the transform. But wait a second, because This is how we set it up initially. But in our case, this will not work as expected. Look what happens here. It's simulating very nicely, but it's only simulating the state of the very first frame. You see, on the very first frame I have 5 dents here, and these are simulated. But where are all the other dents that are created? Well, the problem is that this object here, the ripple object, is created on frame 1, and it reads the data on frame 1. But after that, it does not update the data. So we have to find a way to update the data to make the ripple solver see the changes in our geometry. And that can be done by using a reverse paradigm, as the ripple solver really just inspects the differences between these two states of the geometry. It doesn't matter too much if we put the dents in the initial subpath or in the rest subpath. We can just put it the other way around. Then the rest geometry is deformed and the initial geometry is not. It's really not that much of a difference. It is a difference because the solver is inspecting the rest geometry to determine the curvature and stuff, but it's not that much of a difference. The benefit of doing this is that we can tick this here, use deforming rest. And what this does is that it updates the rest geometry in every frame. Of course, we could stick to the initial subpath and update this with a multi-solver and the sub-solver, but it's way more complicated than just doing it the other way around and just ticking this. So let's do it. So instead of using the undeformed geometry as rest and the deformed geometry as initial, we do it the other way around. So here we use a transform, and on the rest we use the point warp because this is a actually deformed geometry, and then we tick use deforming rest. And let's see what happens. Hey, look at this. Rain on our plane. Because now we have this rest geometry update in every frame, and that means that it's simulating every dent that comes into play. And there you have it. That's basically it. This is the ripple solver. Now it's creating these dents here. Very nice. What we can do now to make the effect a little bit more apparent is go one level up and just append a transform here and just scale it to say 2 in Y. But before we do this, we quickly click move centroid to origin, then get rid of the translate, and then do this again like so. Makes the effect more apparent, as you can see. And then maybe let's append a smooth, because then we get away with less geometry. Go up with a cutoff frequency to make it really smooth everything. And 5 smoothing iterations might do. And look what you have now. Very nice dents. Maybe too many, because the surface is really getting very, very noisy. So time to tweak the parameters of the simulation. And let's quickly pin this view here to stick to this view, although we are inside of the .NET. Go to the ripple solver. And the most important parameter here is conservation and wave speed. Conservation is just the conservation of energy. At the moment, this conservation is set to 1. That means no energy is leaving the system, and that's why we're getting so many waves. So if we go down to 0.3, say, the ripples are fading away a lot earlier. Even more may be good. So let's say 0.2 and then a wave speed of 0.3 to make them slower. And now we have more of a raindrop effect. Let's simulate for a second, and then we can have a look from a different angle maybe. And that's the basic effect. That is how you create raindrops on a pond surface. For the scene I used as an intro, I did a lot more customization. I introduced wave speed, point attributes, and I used the geometry of the rocks to make areas of this water repel the waves. But that is something for part 2 of this tutorial that might come in the future. For now, this is a basic technique, so have fun with this, play with it. I'm looking forward to see what you are coming up with. Thanks a lot for listening, and see you next time.